did not anticipate I would have to travel, at least not during class time. It's supposed to be a trip at the end of next week, and then I'm actually going to Brussels. I'm going to be talking to a bunch of EU policymakers about whether or not encryption should be kept legal or whether the EU should make policy to actually block encryption. And so, as much as I hate to not be here, and I enjoy teaching you guys, I kind of figured that was important enough to miss class. And unfortunately, the way the travel works, I have to miss Monday and Wednesday, which really sucks. However, the good news is my graduate student, Alicia, is going to come in and do, at least on Monday, an introduction and an overview of group theory, simple group theory, and Diffie-Hellman and public key encryption operations. So you guys do not get to miss class. I don't have anything lined up for Wednesday yet. If I can't get something lined up, we may actually not have class on Wednesday, but I will give you lots of notice by email. I hope that doesn't happen. So apologies about that. I hope that's a good enough excuse. The other thing is today, I have to postpone my office hours until tomorrow. Nobody ever shows up at them. But if you were planning to show up, I'm going to have to postpone until tomorrow afternoon at the same time because I have a kid thing. So other than that, that's housekeeping stuff. There's going to be another part coming out to assignment 2. I'm going to talk about it today, and I'm going to get it to you guys in the next day or two. And the deadline will be a little further out for turning the whole thing in, or turning that part in. Any problems or questions with assignment 2, part 1? Yes?
Yeah, well, so I don't remember the RFC numbers, but I was going to key out. So like basically the first first RFC said, hey, we want you to do this kind of padding, and so and then move this thing around, move that thing around, then apply this thing. Okay, perfect. So this will allow divisible by 512. I have the 1 bit, I have padded 0, I have my 64-bit integer, and my message is that one. So you're not giving me.
This is HVAC. Yep.
Right. Yes, this is the HVAC. So and then it says refer to, I think it's like 2091 or something for the actual use of the SSH 256. So anyways, at that point, I've modified, or I've copied my key. The RFC says to append your message to this thing, then append things to that, and so on. So I have actually, either I am copying my entire message and then doing things with it, and then I am, according to the homework, taking our original message M and then padding that one.
So I saw this question. I was going to write back to it. The question you're asking is the padding that's in the assignment, referenced explicitly in the encryption part of the assignment, different from the padding that's deep down inside the HVAC?
Right.
And they may actually be similar. They may even be the same. But logically speaking, the reason that we specify the encryption padding separately, even though they may actually involve reusing the same code. If you reuse the same code and it's right, I don't care. But the reason is that oftentimes when we really implement things, we don't re-implement HMAC from scratch. Like we take an HMAC library routine, and then you pretty much have to go off and implement your own padding. So if it turns out, and I can't tell you this is true, but if it turns out that the padding inside HMAC is exactly the same as the padding I've told you to implement, which I don't think it is, but if it is, feel free to reuse that code. But what is the question? Yes?
So that padding is different. The question is, do we take our padded message and then we put that into our encryption, or do we take our original message?
The structure, I believe, if I remember correctly, is the original message, concatenate the HMAC tag, which is, SHA-256 or 32 bytes, concatenate tag.
And that is your PKC.
Yeah, that is the, bytes, right? Like a series of bytes that will get you up to a multiple of the block size of AES. Okay, so this T, right? So this HMAC is kind of a black box, right? HMAC SHA-256. I don't really need to think very hard about what's going on inside there. I mean, I assume you guys do, but I don't, so that's great. And so we're going to stick M in there, and we're going to basically, whatever 32 bytes come out, that's here. And then there's separate padding. And you're right, there's some padding in here too, but not my problem. You guys can think about that.
Okay, the other thing I asked was that involved like actually copying the full data, and that seemed like something I wouldn't do in like an encryption setting because of performance issues.
Yeah, don't worry about performance.
Okay.
That's a simple thing. Get this spec working, make sure it works, and it's byte for byte correct, and that's it. Okay. Yeah.
Can we assume that our message comes in bytes instead of bits because the RFCs?
What's the difference?
The difference is that I don't know how to read. Well,
your message is going to be a multiple. It's going to be a bunch of chars. It's going to be a multiple of 8 bits. So I'm not going to give you like a 7-bit message to encrypt. No problem. Don't worry about that. In practice, you're really only going to have to work with bytes in this assignment, except like maybe deep down inside some of the functions bits. But like, none of the padding is going to be bitwise, bit size. Good. Any other questions? Okay, so far I'm hoping this will be a simple assignment. Feel free to use, libraries to check your implementations. Like if you want to use someone else's implementation of HMAX, check yours. No problem. No problem. Just don't turn in somebody else's implementation of HMAX. Good. Okay. Good. Any news? Anything going on in the world? Crypto-ish, preferably, but maybe not crypto-ish.
There was the options bleed. I don't know. I don't know. It doesn't seem all that serious. There's a bug in Apache where if you have a improperly configured htaccess file, then sometimes when you send an option request, you can sometimes get back small amounts of RAM that you shouldn't have access to. But it's not deterministic. You don't control how much you get, and sometimes it doesn't give you anything back.
So who thinks that's really scary and who thinks that's no big deal? Show of hands. Big scary. You guys are you're just hoping that I'm going to say it's scary. Okay, what about the not a big deal crowd? Don't worry, it's okay. I'm not going to get mad at you. Okay, so you're right. So you only get a few bytes. I don't know how many bytes actually off the top of my head.
It's
okay.
It doesn't. They never got more than like 50 bytes.
Okay, so and it's random, you said.
And it's random. It's out of the Alexa top 1,486 were vulnerable, and out of those 486, they were unable to get it to fail every time.
Okay, but were they able to get different bytes from the server memory, different ranges of the server, a particular server that was vulnerable?
Yes.
Okay. So first of all, what is inside of server memory that we care about? What kinds of stuff live inside of a web server memory?
Keys.
Keys, good. Cryptographic keys, like your SSL private keys. If you were to steal somebody's SSL private keys, what could you do? TLS, SSL. We haven't really talked about this yet, but this is the encryption protocol that encrypts web connections. What could you do with those keys? Anyone know?
Fake a server.
Okay, yep. One thing you could do. You're gonna say the same thing, or?
I was gonna say a hijack.
Good. Okay, so you could basically pretend to be a website, and if you're on the person's network communication path, it's an active attack. You could pretend to be Amazon.com or whatever, and then you could have them connect to you, and then you could steal their password and maybe steal their credit card number and all sorts of bad stuff. So that would be one thing. What else could you do with a SSL or a TLS private key? Yeah.
Decrypt all communication to the website.
Good. Can you do that? That is a question. With a long-term private key in TLS, can you decrypt passively? So I know you can do this active interception attack where you pretend to be Amazon, and then presumably you can decrypt everything. But can you passively decrypt a connection if you're just an eavesdropper and you have Amazon's secret key?
Does a Viking backer attack what
No fancy attacks.
the
Just
1,000 message attack?
that's a separate issue. We'll talk about that in a bit. But what else? What can you do? Anyone? Yes.
Can you record the packets that you see and then
Good.
store them and then?
That is definitely a prereq. So maybe I'm on your Wi-Fi, I'm recording your encrypted packets going over the Wi-Fi. It's like an unsecured Wi-Fi network. It's encrypted though, your connection to Amazon's encrypted. I record them all. I have Amazon's secret key. Now what can I do? So can I decrypt? Can I decrypt those packets? Okay, well the short answer is it depends. Okay, so there are different handshakes that are part of the TLS protocol. One handshake, which we'll talk about in a little bit when we actually talk about what these encryption schemes are, uses RSA. And what it does is basically you have a client and a server, that's Amazon. And the client generates something called a pre-master secret, PMS, which is a 48-byte random key, sends it over to the server encrypted under the public key of the server. Oops, sorry, PMS. And then there's some other stuff, and all of this stuff gets hashed together, like there's some random nonces and some other junk that shows up, whatever. And that gives the encryption key that both sides use to then send data. So if you have the secret key, and we haven't talked about public key encryption much, but trust me, if you have the secret key for Amazon, which you've stolen, you can now decrypt this message, you can get this PMS value, you can now, because all the other stuff is not encrypted, you can now compute this hash value, and you can get the key that is going to be used to encrypt the data, and without ever blocking or modifying a packet, you can passively decrypt everything that goes across the wire. However, there is another flavor of handshake that is allowed and is increasingly the norm in TOS, and that handshake is, we're going to talk about it, or Alicia's going to start talking about it on Monday. It's Diffie-Hellman handshake. And what you need to know about Diffie-Hellman handshakes is the following. The long-term key is not used to encrypt. The long-term key is used to sign. Roughly speaking, both sides make a temporary key of their own. So we'll call this PKT, SKT, and another one. This is a very weird way of expressing it. PKT prime, SKT prime. And then they basically encrypt messages to each other using these keys and using digital signatures to prove that these are actually the right keys. I'm not going to go into all the details, but the gist of it is, if you steal the long-term key, you can intercept this and you can pretend to be Amazon. That active attack works, but the passive decryption attack does not work. And so the simple answer is, if you can steal someone's secret key, it's very bad. How bad it is depends on a lot of things. However, who chooses which of these two modes, the RSA one or the Diffie-Hellman one, you're going to use when you make a TLS connection to Amazon? Who chooses that?
Client. The client will choose it, because it depends if the client is compatible.
So maybe that's, so who thinks that's not right? Anyone disagree? There's only one other answer.
I feel that the client sends all the suites that it supports, but then server chooses the highest
Good.
one.
So it's really both get together. But if you are impersonating Amazon, or you can somehow mess with Amazon's messages, it's possible. This turns it back into an active attack. But you can potentially, in that setting, kind of edit the messages, or you can edit the client's messages so that the client looks like it doesn't support the Diffie-Hellman thing, and then the server will choose RSA. So there's kind of this spectrum of attacks from like just straight on impersonation to slightly tampering to like really just, to passive. It really depends on how these things work. Anyway, getting back to options bleed. Stealing a server's memory sounds like a big deal if you can get private keys. What else lives inside of a server's memory, a web server's memory? Yeah.
If it's a shared host, whoever else, random things from whoever else is on that host.
Good. And do you remember Heartbleed? Anyone remember when Heartbleed came out? What was the advice everyone gave you after Heartbleed? Change your private keys? I'm talking about you guys as consumers. What was the advice? What's the advice they always give you after a security incident?
Change your password.
Change your password. Why did you have to change your password after Heartbleed? What else lives inside of that server's memory if it's a shared host, right? All sorts of junk was sitting there. Previous packets that had gone through. Sometimes if it was just a load balancer that was terminating SSL, then that thing had your passwords, had other people's stuff, maybe another website stuff. So yeah, short answer is lots of stuff lives in memory. Okay, last question about options bleed. Let's say you only get 50 bytes or less than 50 bytes of memory from the server each time you make a request, but they're randomly located. Do you think that's useful, exploitable?
So the 50 bytes aren't necessarily contiguous?
Yeah, the 50 bytes, let's just say they're anywhere in memory.
That makes a very, very large, complicated assembly problem where you have all these different strings you have to stick together somehow.
Can you solve that problem?
It's NP complete, at least generally speaking.
Do you think you can solve that problem in just a simple way?
No.
Well, people did with Heartbleed. There was a limit to how much memory they could get. They were able to get chunks, and it turns out that they were basically able just to look and find, overlap. Whenever they got an overlap, they could recognize it relatively efficiently, and they could put things together. So nobody's built a full exploit as far as I've seen for options bleed. Maybe somebody here should do that as a class project. That would be really cool. But basically, in some cases, when you get these kind of random memory leaks, if they're really randomly located, you can basically build a patchwork of the server, and you can slowly reassemble it. It's kind of like getting little pieces of DNA and finding where they overlap. It doesn't work very well if they're small, but it may work well if you get pieces that are large enough and have unique enough information in them. So you could actually build a map of all of RAM, and then wham, you look for private keys. Okay, one more question. Actually, no, I'm not going to ask this because we haven't done public key yet.
Right, my question is a new news thing. I saw that like 130 million passwords from Troy Hunt's Halligan own website. And I actually downloaded the file, I looked through, and then you see all kinds of what vulnerability actually happened there? Like, what is that?
Good. Okay. Does anyone here want to explain to me password hashing? Anyone know how password hashing works? How do we store passwords on a web server? This stuff's great because I get to like lecture at you and you get to give me news. Yes.
Well, usually they don't store it, like, sometimes they take a hash, they take the actual hash of the password, so it's never actually, password's never stored.
Good.
itself.
Why don't you store passwords on a server?
Well, then you know what the password is, and if it gets compromised.
In the olden days of Unix, meaning like 70s and 80s, where were passwords stored on a Unix server?
In the password file.
Right, and were they like hidden? Who could access them?
The admins.
Anyone could access them, right? So this was the problem that the Unix designers had. And they said, this really sucks, because if everyone can see the password file, this is a big problem. And so what they did is they came up with this idea, which you just described, which is instead of storing them in clear text, we'll do something to them, we'll encrypt them. The problem is, what do we encrypt them under? And they said, well, we don't really know. So they came up with this transform, which they called the crypt function. We'll call it crypt. And you'd put a password into it. And the basic idea was anyone could compute this crypt function, and it would produce some sort of, let's call it C, but it was deterministic based on the password. And what you would store was a bunch of these values C. When somebody wanted to log in, they would present their password, and this C would be stored in the password file. And then they would type in their password, the system would recompute this crypt function on that password, check to see if it matched their on-file password, and things would be good. And then the system would know whether or not you were allowed to log into the system. And the theory was that if this crypt function was hard to invert, it was a one-way function of some kind, then nobody who got this password file would be able to break it. Now in practice, is that true?
No.
Okay, what is the attack?
Rainbow tables?
Before we get crazy, don't do it jumping straight to rainbow tables. What is the generic attack?
Collision attack.
Not a collision attack. Yes.
Just transfer transmit
That C value?
yeah,
Transmitted to who?
wherever it's supposed to go on, to the computer.
Oh, no, I want to know how I crack. I've stolen an Etsy
Oh.
password file. I want to know how I get the passwords that are in there. I said crypt is not invertible. You should not be able to take a C value and undo whatever crypt does and get back the password. Is there any attack? Yes.
You could try different permutations and then use the hash function and see if they match.
What do you mean by permutations?
Like just guess random passwords.
Ah, okay, good.
Try PASSWORD and see how many matches you get.
Good. So what is this called? I hope somebody said in there said dictionary attack. Good, so I make a dictionary of very common passwords. I compute the crypt function on every single one of them, and I compute a candidate value C for each one, and I check it against all the values in the password file. And if I find one that matches, wham, I know that that person used the password or whatever. Okay, great. So this was like the first thing people thought of. How do you harden this up a little bit?
Salt.
Good. Okay, salt. What does salt do? What is salt? Yes.
And when you crypt password, and then inside crypt it throws some deterministic random stuff into it, and then
Deterministic random stuff.
no,
That
doesn't make sense. But you add stuff inside of the password so that the hash that is stored does not map perfectly to the password.
What is the attack we're trying to block here? So remember, the attack I just described is I encrypt the word password, and I put it through crypt, and then I look through the entire file, and I look for anything that matches it. I don't have to like go user by user. Yes.
What it prevents is somebody. Oh, I'm sorry.
No, fine. Just go ahead.
What it prevents is somebody having the same password, comparing the hashes, and realizing.
Okay,
from
good.
that with
So
a-
there,
with
if two
different
different
passwords.
users used password, then we
Right.
would see the same hashes. Good. Yes.
Yeah, also we have avoid rainbow tables.
Good.
Because
I know you guys love rainbow tables.
No, it's more about to avoid attacks where already implemented automatons.
Ah, okay. What is this kind of attack? Somebody explain this attack a little bit in a little more general terms. Don't say rainbow tables. What does that already implemented mean? I want to mix it up. Somebody else. Anyone? How do I, if I'm an attacker, how do I make this attack? Right now, this attack involves stealing your password file and then running through and running this crypt function on a huge dictionary of passwords, which could be like billions of passwords long. Yes.
Just make the crypt function take a while.
Okay, we haven't gotten there. That is coming. but I'm the attacker. I don't want to, after I steal your password file, run a billion instances of this crypt function. So how do I speed my life up so I can attack lots of passwords quickly? Yeah.
Yeah, actually I just compute tables.
Compute tables. So
Which could match, and then I just run the password file through those tables.
good. So I don't, in this system, I don't have to steal the password file first. I can build a huge pre-computed table of my dictionary. I can run the crypt functions. It's public. It's Unix source code. I can run crypt on every one of my possible things, store that in a huge database, and now when I steal your Etsy password file, all I have to do is a bunch of lookups against my pre-computed outputs of this crypt function. That's fast. Great. Now, with that knowledge in mind, what does salt do? Shoot, go ahead. You brought salt into it.
So what salt does is you take a value that is unique to your Etsy password file, and then when you crypt, you don't crypt password, you crypt password plus salt. So
Good.
that breaks tables because they have to recompute the table for whatever your salt is.
Very good. And so what this does is it adds a bit of uniqueness. Salt is really a random, and I'm going to often use this to indicate random. You know, it's some bit string, I don't know how long it is, maybe we'll make it 128 bits long. It's randomly sampled, it's a random string. And so the idea is I can't pre-compute a table anymore because I don't know the salt that's going to be in that particular file. And so there's nothing I can do until I steal your Etsy password file. So it makes me, so I can't like amortize my work. I can't build one big table and then use it for every server I attack. I have to do it on a per server basis. In fact, we can go more than per server. We can go per account. We can make a unique salt for every username password combination. Where do we put the salt? Where do we keep that salt? Because we need to be able to recompute. When people log in, we need to recompute this crypt function. Where do we store the salt?
Salt is deterministic, like it's the username password.
No, it'll be random.
No, it's stored in the shadow file.
Okay, good. Or we can just store it in the password file. We'll just store it right next to
Right.
C. And now when somebody logs in, the salt's right there. It's not secret. That's why, we don't call it, like secret key or something. We call it salt. It's just sitting right there. But when somebody logs in, we have all the information they need when they type their password to do this check. But somebody who's trying to do some kind of cracking operation, for each individual user, they would need to recompute all these crypt values. They could not do it once. Okay, so lots of people have screwed this up. Unix initially didn't have salt, they added it. Microsoft, all of these old, what are they called? There's an old hashing protocol that Microsoft uses, like NT-auth or something, still used in a lot of stuff. Didn't have any salt. And so these things actually are vulnerable to these kind of attacks, pre-computation attacks. You'll hear people say rainbow tables, that's a fast way of doing it. Okay, good. Last question. Now, somebody said this. So let's say we add salt. There's still an attack. What is the attack? Just remind me. It's not a hard attack. We've already described it. Say we have salt in our password files. Can anybody break in and invert these passwords if they steal an Etsy password file? Yes, they can. All we've done is slow them down, right? They can still run a dictionary attack after they steal the Etsy password file. After they've got my salt and my C value, they can just take a really big computer and do a dictionary attack live, compute each crypt value. How do we slow them down? How do we stop that?
Why don't you change the salt values every now and then?
Well, we could do that, but that's not really going to help because what they're trying to do is they've stolen the password file. At this point, we can't change the salt value, right? Like they've got C and they've got salt.
Right, and then like change the salt values and then recompute C.
You can, but it won't really stop them. It won't actually stop that attack.
Okay.
Yes.
Public function take a while.
Good. Okay. The next phase of evolution in password functions was make this password computationally very expensive. How do you make a function computationally very expensive? Well, you put it in a for loop and you run it a lot. So you take the password, and there's lots of ways to do this, take the output of that, run the crypt function again on that output, and just make it so you have to go around 50,000 times. And that is actually something, one example of this, in case you're interested, is a function called pbkdf2, password-based key derivation function 2. You can set an iteration count on that, 50,000 to 100,000, and it's slower. Good, have we solved the problem? Are we done? Come on, guys. What is the attack on this?
More compute power?
More compute power. Now, what kind of compute power?
Special hardware.
Somebody back there.
Could you parallelize it?
Good, parallelize. Good. This is embarrassingly parallel. We can do every single password in the system. We did 300 million of them on a different syscore. We might even be able to try the dictionary space, break the dictionary space into lots of chunks. Good. What is good for parallelizing things?
GPUs.
I heard GPUs. That's true. GPUs are good for parallelizing things. What else?
A6.
ASICs. What else?
FPGA.
FPGAs. Okay, so we have lots of options for parallelizing things that seem computationally expensive on the CPU. We can just throw hardware at the problem and they get fast. Okay, so I think that the answer to your question that you started this whole thing off was how did they break all these passwords? I think that they were just using SHA-1 for the hash function, for this crypt function. I don't think they were even using PBKDF2. But okay, one last iteration of this. And this is an arms race. How do we stop the attackers who have GPUs and FPGAs and ASICs? What do we as system designers do to make their hardware not good? Yes?
Force it to be, make the function unable to be parallelized. Require some sort of,
Hardware dependent function.
Because remember, the function itself, making that non-parallelizable is half the battle. But remember, they can still parallelize the dictionary search, right? If they have to call that function 3 million times, they could have 3 million different parallelized instances of that for each input. So what you're saying sounds right, but it's not quite clear enough to me. How do you make this hard for somebody to throw FPGAs and GPUs at? Yeah?
You just make the output of the crypt function bigger?
Then you just need a bigger FPGA or a bigger GPU. Something else. You're kind of getting close to it. What is not easily, so computation for specific functions we know scales very efficiently with ASICs and FPGAs. Does anyone know something that a computer requires or has that does not have quite that same kind of scaling function? Yes?
Memory.
Memory, I like it. How do we use memory?
If you make it expensive and require the function to store a lot of data in memory, say if it takes 1 gig for one computation on a server, it's probably not a big deal, but you can't really parallelize that beyond a certain extent.
Fantastic. And in fact, that is the answer. You've just invented a function called scrypt. And scrypt is a function that literally does, you not only feed in an iteration count, it actually uses PBKDF2 at the bottom, but you also feed in the amount of memory you want it to use. And what it does internally is it makes this big pseudo-random array, sticks it in RAM, and then does a lot of operations where it kind of hops around using the fact that RAM is random access to hop around to different places in memory. And it's very fast if you use the memory. You could simulate, of course you can always simulate a big memory by doing some kind of deterministic computation, but if you do that, the actual computational time explodes for that function. So scrypt is the state of the art for this kind of password-based system. Since I'm wasting a lot of time on this, what else might you do if scrypt doesn't save you? What else could you do? Let's say you just, there is no amount of computation that you think your attacker isn't willing to spend on this, or no amount of money. How else could you keep these passwords secure?
A hardware dependent function.
Maybe you could do something like secret in your function, but remember, we never want to make hardware secret. You could make a hardware dependent, but then they could just build hardware or an FPGA or something. So what else? Mix it up. Is there anything we could keep secret? Right? So we've made the assumption that salt is public in the sense that if your database gets stolen, your salt gets stolen. What if we stick, and then maybe this is kind of what you're going for, what if we stick that salt, or we stick some kind of secret key into a piece of hardware that is maybe separate from the system, which is kind of what you're saying, and we put that secret key somewhere that it won't get stolen, or we encrypt the salt. And sometimes when people do this, they take the salt and they make it secret, they hide it inside of a piece of hardware, and the name is called, I don't really like this name, but then they start calling it pepper, whatever. Okay, so if you ever hear somebody say pepper and it's in reference to password hashing, they're talking about secret salt. It's hard to do that. You have to make assumptions that you can keep secrets after your database has been stolen. Typically that involves hardware, or storing the key somewhere else on the system that hopefully your attackers won't find it, but that's kind of security through obscurity. Anyway, so this is why password hashes get broken because of this. Oh, by the way, one more function I should mention, bcrypt. falls into the same kind of category as PBKDF2. It uses Blowfish, but it's also computationally expensive. You will see all three of these, or 4 or 5, or whatever I just put up here, as we go through this class and in the news. Good. Okay, good, fun. So let's get back to authenticated encryption. All right, we were talking last time, and I posed you guys a challenge. And the challenge, I hope, is an easy challenge, but let me, actually, we don't need this right now. The challenge was that we had 3 different ways of combining encryption schemes, which I said we could assume they were semantically secure, meaning they were secure under chosen plaintext attack. And we were going to try to combine them with MACs. Quickly remind me, what is the profile, what does a MAC algorithm's input-output profile look like? Very quickly. We have an algorithm, it's called MAC. What does it take in? And what else? Good. Key, message, and what does it spit out?
Tag.
Good. Sometimes people call it a MAC. I'm calling it a tag just to disambiguate a little bit. Great. So that is the entire thing. And when we verify, when somebody sends us a MAC, how do we verify that if we have the key, how do we verify that MAC is correct? Yeah, we recompute, given the message, we recompute this, and then we check to see if it's equal to the tag that they sent us. Fantastic. Now, I gave you guys 3 different options for how these things could be strung together with encryption. Name one. Somebody.
MAC then encrypt.
MAC then encrypt. Okay, so we would compute the MAC, we'll call this T, is MAC of K, M, and then you're going to encrypt. Ciphertext is encrypt, message, concatenate, tag under K, and we'll only send C. Sorry, that notation's a little confusing. We're only going to send, is that what you were thinking?
Yes.
Good, okay. And we call that MAC then. MAC then encrypt. What was another?
Encrypt, then MAC.
Encrypt then MAC. Okay, we would compute a ciphertext is equal to encrypt under K. I'm sorry, I should be using different keys. I promised you I'd use different keys, so we'll call that K1. Encrypt the message, and then what are we going to feed into the MAC function? Okay, I think you guys just said MAC, K2, and C, and we would send CT. And this was called MAC, sorry, I forgot. This was called encrypt and then MAC. Encrypt, then MAC. Okay, give me a third one.
MAC and encrypt.
How does that work? I have literally forgotten. I do not know.
You
Tell me.
concatenate them.
You can catenate them. Okay, I like that. All right, so what are we going to do? Let's compute the T is MAC K2 message. Good. And C is equal to the encrypt under K. Oh, sorry, I'm mixing up my keys. Under K2 of the message, again, concatenated with T, and we would send C, or whatever. Hope that notation is. You can notate this a lot of different ways. And you guys said this was what? MAC. Oh, it's encrypt and MAC. All right. Now, last time somebody pointed out a problem with encrypt and MAC, I seem to recall. And they felt that it somehow was not very good. Why? What is the problem with it? From the point of view of we want a strong encryption scheme, what does it reveal?
If you're able to decrypt, like you have a key or something, and get the plain text, and you can just recompute the tag.
Yeah, but well, wait a second. How do we do that? I mean, you get the tag, it's clear text, right? We're sticking it on the end of the message.
Oh, I was saying if you want to edit the message.
Oh, but like you'd have to have the key, so let's not worry about that. So let's assume that you are an attacker who doesn't have the keys. What is that? What information does that leave?
You could keep making the other person drop the message by screwing around with the T, like at the end of it.
Nah, but you can check the T, right? The T comes across. You're sending C, which includes this T. You can check the tag. Seems like you can't screw with anything. Yep.
The relation between the ciphertext and the tag.
What does that mean?
with the same messages, it will always be a specific tag and a specific ciphertext.
Very good. So you're pointing out that the MAC scheme is deterministic. That means T is going to be a deterministic function of the message. And then since T has been kind of glommed onto the ciphertext, what do we know about deterministic encryption and semantic security? Is it semantically secure? Can never be, because there's always an attack. And it turns out if you implement the scheme and try to play the semantic security game, it becomes totally insecure. So we've actually made encryption worse somehow by adding a MAC. Let's not do that. All right, so that leaves us with no encrypted MAC. We have two other directions to go. All right, MAC, then, let's see, MAC, then encrypt. Let's look at that one. How do you guys feel about that? The top one. Anyone have any thoughts? Yes.
It's decent, but you have to decrypt to tell if your message was messed with.
So you're going to have to like use your decryption key, and then you might find out that actually the whole thing was screwed up. Okay, that's a fair point. So you're kind of exposing your decryption key. That is 50% of the problem. I agree. That is definitely a problem. Is there anything else that might go wrong with it? The problems here are a little subtle. Yes.
You can deny the message even if it is right. Like you can just change the MAC and deny the message even if it's right.
You can deny. Well, but I mean, you mean the decryptor can deny the message?
Yes. Well,
I mean, you could always, like, the attacker can always scramble the message and make it look invalid. So that's not a new problem here. And the decryptor, we're assuming they're being honest. They're part of the system. So I don't know about that one. Anything else? Let me make this a little work. We've been vague about what the encryption scheme is. But let's imagine that the encryption scheme, just for generality, let's say that our encryption scheme is CBC mode. Okay, what happens in CBC mode? If your message is not a perfect multiple of the block size of the block cipher, what do you have to do? Pad it. Interesting. Okay, hang on 1 second. Okay, so let's say I have, what's actually going to happen is we have our message. We're going to concatenate it with a MAC tag. And really, we're going to end up concatenating that with a padding. Call that pad. And then in CBC, we're going to encrypt all of this stuff under some key. Okay. All right. And the tag, by the way, is computed over this message. Does anyone see anything that you could do that seems kind of bad to this message? I mean, I think this is not an obvious thing. And I mean, geez, up until about 2001, which means like 30 years of cryptography, nobody saw anything wrong with this approach. So do not feel like this is something obvious of what you have to do. Can you tamper with this message in any way without it being detected or rejected by the MAC element? Tamper with anything? Right? Yes.
You mess with the pad.
Good. You can mess with the pad. That is true. So let's say that the padding scheme is not structured. Right? So you can definitely maul if it's a malleable scheme. In fact, let's make it easier. I'm going to make our lives a little easier. Let's say it's counter mode because we know that's really malleable. Okay, let's imagine that I can mess with the padding in some way that doesn't cause the padding check to fail for now. Okay, so I can do this kind of mauling of the ciphertext to make a new ciphertext that will decrypt fine. The padding isn't broken, it will decrypt fine, the padding will be taken off. The MAC will still check out because I'm not messing with any of the message or the MAC tag. So I can kind of mess with the ciphertext in such a way that I get a new ciphertext, but it still decrypts fine. So what? Doesn't seem that bad, does it? Huh. Okay, so we do know, I mean, this is a big deal. Cryptographers pointed this out, theoretical cryptographers, and they said this seems kind of weird that you can kind of maul messages. In fact, there are other schemes that are even more malleable, like you can change the whole message, the whole ciphertext in such a way, like re-randomize the ciphertext, not CBC mode or counter mode. But there are encryption schemes where you can totally, as an attacker, without knowing the keys, like really, really mess with the ciphertext so that it will still decrypt the way it normally would. And all of these schemes will work fine in this MAC then encrypt mode because you're not messing with the plain text. This is called benign malleability. It doesn't mess with the message. Nobody cared. The entire theory, the entire applied crypto community yawned and said, who cares about this stuff? As long as we're checking our message, who cares if you can mess with the padding? Like, dumb, this is stupid. But then in 2001, somebody came along and they showed what is probably the coolest attack in, one of the most useful attacks in symmetric crypto. And they pointed the following out. They pointed out that sometimes you can learn something useful. Specifically, let's imagine that our padding scheme can be changed in interesting ways that allow us to get a distinguished message when the padding doesn't check out. Now I'm going to show you a particular padding scheme that should look very familiar. The padding scheme that they pointed to was used by SSL. This is back in 2001, a guy named Sarah's Bottom. What he pointed out was that SSL uses this thing called PKCS5 padding or something very like it. And you've seen this before if you've already looked at the assignment. Let's say that you need to add 5 bytes of padding to the thing. Well, the way SSL does this is it adds padding that looks like this. Okay. All right, great. So we've added 5 bytes of padding that looks like this. How do you check this padding? When you decrypt, how do you check and remove this padding?
You check the last byte and then remove that many bytes of that value.
Good. So you look at this 5, you say there must be 5 bytes of padding, and then you strip away all those bytes. In fact, we can even get more specific. There's different ways of doing it, but let's imagine further that the verifier, the decryptor, actually checks that all of these bytes are 5. And it sends back an error if any of that does not look right. It says padding error. Okay, so if one of these bytes is 6, bad padding. If they're all 5, good padding, we move on. And then we check the MAC, and then we'll send back, if the MAC is bad, we'll send back a different error, a MAC error. Okay, now that I've given you this much, is there anything bad we can do? For an attacker, this is AES counter mode. We can maul it. We can change any bits we want of this ciphertext such that the same bits will be flipped in the underlying plaintext. Yes?
If you know whether or not the receiver is accepting it or not, you can keep changing the last bits so that you can kind of figure out the bits as you go from the end.
Good. What can you learn? What's the first thing you can learn very easily?
You learn the MAC and then you start chip flipping.
Okay.
You have an oracle which says it's the wrong MAC or the right MAC.
Let's take this one little step at a time. Let's say that I'm an attacker and I see a ciphertext. It's literally opaque to me. I don't even know how long the underlying message is, how much padding there is. I just get this black ciphertext, okay? It's a black box. How do I figure out, first, how much padding there is on this message?
Just encrypt 0 to F, just encrypt and put it in the padding at random positions.
Okay, at random positions. Give me a more systematic approach.
This is the last position.
Okay, so I could change one bit in this last position. Okay, and what's going to happen if this last byte is always a padding byte, let's just say, because we're just going to assume that. What error am I going to get if I do that?
Padding.
Good. Now, what if I mess with a bit in this one? What error am I going to get?
Again, same thing.
Well, it depends on how long that padding is.
Good. If the padding was only 1 byte long, right, then I'll draw a different message. Then it would look like this, and this would be the tag for the MAC. So if I mess with this byte, and the padding is 2 bytes or longer, now I'm going to get a padding error. But if the padding is 1 byte long, I'm actually going to get a MAC error because I've just broken the MAC verification. I've messed with the MAC. Do we agree on that? Okay, good. And of course, this generalizes. If I get a padding error here, I can try this one. I can keep trying. And we're assuming, by the way, that I got one ciphertext, and then I'm sending different versions of that ciphertext to you, and you're willing to decrypt them and send me back an error, either a padding error or a MAC. So that's the setting. I'm an attacker. I get one message that's encrypted. I can't see. But I can send messages to you to be decrypted. I can observe what errors you give. Okay, does everyone agree that I now have a strategy for learning something about the length of the pattern? Learning exactly the length of the pattern. Does anyone think that's useful? Yeah.
Well, yes, I heard about the oracle attack that you can use because you know already something about the message. So it's like somehow, it's like not the whole message itself, but what is encrypted. Like the padding is also encrypted.
Okay,
so
what you're saying to me is that the padding is supposed to be encrypted. It's supposed to be secret.
Yes.
I should not be able to learn something about it. And here I am learning something about it.
Yes.
This seems bad. But it's not that bad, right? All we're learning is like one little thing, like the length of the message. But I agree with you, it seems really bad. Yes?
If you flip the padding from 5 to 6, then you can learn the last byte.
Ah, okay, good, good, very good. So let's say this is our initial message, and I think what you are saying is, once we've learned the length of the padding is 5, and we know all the bytes of the plain text. We know they're 5, up from here to the right. 5, 5, 5, 5, 5, 5, 5, okay? I think what you're saying is, okay, well, we also have the ability to change the ciphertext, to maul the ciphertext, to flip bits. So what if we do the following? We know this is 5. What if we flip one bit of each of these bytes to turn this into a 6? Well, it doesn't seem very useful. But what are we going to learn if we do that? We are going to learn something, and it's going to be interesting. Yes?
What about the encryption?
We are going to learn something about
The encryption changes when I like flip bytes.
The ciphertext changes, the decryption would change, these padding bytes would change into 6s. What would the verifier do?
Like if the tag is
check plus
tag
tag.
is 6, it's gonna accept it.
Good. If the last byte of this tag is 06, that's valid padding. We are going to get a valid padding condition, which means actually it's going to move on to the MAC check, and that's probably going to fail. So we'll get a MAC error. If the last byte of the tag is not a 6, what are we going to get? Okay, good. This seems bad, right? We started out by like learning this padding, and we were kind of like, well, padding's not a big deal, right? Who cares about learning about the padding? But now we're kind of moving on. Now, admittedly, it's not very useful. All we've learned is whether the last byte of the tag is a 6.
You would be able to walk that back and determine all the bytes in the tag.
How? Wait a second. Because all we've got now is whether the last byte of the tag is a 6. That's not useful. What if it's not a 6?
So I know all the bytes of padding, and I can change those. If I keep changing the values in the padding...
You're skipping a step, though.
Okay.
Because if I keep making the padding longer, and this last byte of the tag is not a 6, is probably, we're going to get stuck. Let's just go with this last byte of the tag. And I want to know, is there anything else I can learn about it if it's not a 6? Shoot.
It's not the one I tried, so we can cycle through all 256.
How? How do I cycle through? How do I cycle through different things other than 6? Like, without, I mean, I can only make this, let's just assume right now I'm making these into 6s. What if that's not a 6? What is the attack? What am I cycling? Yeah.
You can make the one to the left of the last bit of the tag a 7, and then...
I could do that, but if I make this into a different ciphertext, if I turn this into 07, ... then actually what the verifier is going to do is it's going to output whether the last 2 bytes of the tag are 07s. That doesn't seem so great. It's not very useful to me because the probability of that's even lower. So, okay, you're right. There's a little bit more information I can get there, but it seems like the more you extend this, right? Like if I turn it to 8, then it would only give me what I want to know if the last 3 bytes. This seems pretty unlikely. Yes.
Like cycle through the last byte of the tag.
I like the cycling through. How?
Like flip bits to like increment the number.
Ah, what number? Tell me which exact byte I want to increment.
The last one.
Of what? Of the tag?
Yeah.
Good, okay. So let's say that the last byte of the tag, I don't know what it is. It's some unknown value. Let's call it TT in hex. Okay, some number. Okay, I've done this test by changing all these to 6s, and it did not tell me padding. It said padding here, which tells me this is not 6. Great. Okay, what if I add 1? Let's just use addition for now. What if I maul this ciphertext to add 1 to this position of the plain text, what's ultimately going to do? So I turn this into TT plus 1. And now I repeat this test with all these sets of 6. And it tells me, again, padding error. What have I just learned? Yeah, TT plus 1 is not 6. And let's say I add 2 to this thing. Okay, I try again. I run another experiment, leaving all these set to 6. And it says MAC error. What have I learned? I've learned that TT plus 2 equals 6. Now, of course, we can't do addition using the mauling that we have is XOR. So we're not going to add 1, add 2. We're going to XOR with 1. We're going to XOR with 2 all the way up to 255. And we're going to repeat the experiment. So we're going to go we know that we have this unknown value, sorry about that, this unknown value TT, and obviously we're going to test first with TT XOR 0. We're going to have TT XORed with 0, 1, dot, 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 all the way, and I'm using hex here just to remind you guys, TT XOR FF. And one of these values is going to say the padding check worked, we got a MAC error. And when we learn, let's say we learn that this value turns out to be the one that actually is the correct padding, meaning this, TT XOR FF succeeds, what do we know this value TT XOR FF is? That's FF hex. I'm going to just keep saying that because it's a little confusing. What are we going to learn? What do we know about this value? It's 6. Good. Because remember, the only way the padding would have succeeded was if this last byte was 6. Because all these other bytes were 6. We made them 6. So we know the following relation, TT, unknown value, XOR FF is equal to 6. Now, what is TT? Yeah, we can just solve very simply to figure out what that underlying value is. So we learned a byte, not exactly of the plain text message, because we're actually kind of digging into T, the tag, but we're learning stuff, and it's awesome. Okay, great. How do we extend this attack to get the next byte of the tag? Yes?
You just remove the byte you found?
Well, we can't really remove anything. All we can do is small things. We can change flip bits. Yes?
Just change the next byte to 6 and try the
6?
7.
7, good. So we do this. We flip all these to 7. Okay. And we take this last byte, which we just learned was, I don't know what it was, but let's say it, let's just say it was EA and hex. Well, we do whatever we have to do. We XOR some stuff in that. Oops, not 6. We XOR whatever we need to XOR into that to turn it into a 7 as well. Oh, sorry, it was, 7. And then we repeat the attack on the next byte moving leftward. And we keep doing that. And if there's 16 bytes in a block, we can do the entire block. And I'm not going to go into how you move on to the next block, but we will be able to move on to the next block in some way. Okay, so this thing is called, and it has a name, it's a pretty famous name in crypto, it is called a padding oracle attack. And the idea, when we talk about an oracle in crypto, what we mean is that there is something that you can send values to. It will maybe decrypt them and give you back a bit of information, just a little bit of information, but literally a bit. And the bit is, did the padding check? Initially, in the early days of crypto, up to 2001, people thought the answer was, there's no way you could decrypt a whole ciphertext just getting a bit of information for each decryption query. But it turns out you can. You can just systematically peel the encryption away. You don't have to know the secret key. You're just learning this a little bit at a time. And this actually worked against SSL servers at the time. It was a very efficient attack. All right, great. So we have an attack that totally Hollywood decrypts crypto. And by Hollywood decryption, I mean like literally you can sit at a computer and watch the plain text pour out, even though you're using 128-bit AES, which is supposed to be, take millions of years to crack. So this kind of stuff actually happens in real servers. So how do you fix it? You've got SSL. You're stuck using the stupid Mac then encrypt, Mac and encrypt. Wait, no, which one is it? Mac then encrypt scheme. And you've got this padding, and you can't just go and change the whole SSL protocol because everybody's using it. You've got vendor lock-in. How do you put a Band-Aid on this? What do you do?
Just send the same message of padding error and
Good.
Mac error.
You're leaking a bit of information when you have this padding error versus MAC error. Just get rid of that and just return one error that says bad. Literally, that's what they did. This is exactly what they did. And it solved the whole problem, right? No. We were fighting this problem as recently as 2014, like practical attacks on SSL and TLS. Why doesn't it solve the problem?
The amount of time.
Ah, time. Time sucks. Time leaks a lot of information. Why does time leak information?
Because if it takes a little extra time, then you know that it went through the tag check.
Good. That's basically it. So, right. So if the padding fails, you're not going to go on and check the MAC because like the padding's screwed up. And so this is how implementations worked in the early days in like 2002. They said, let's just return this one error. But then people immediately pointed out that they could actually tell whether the MAC was being checked just by measuring the time. Maybe they did like 50 samples or 100 samples for each message, but it worked. And it worked remotely and it worked beautifully. So that didn't work. So we need another Band-Aid. What's that thing?
Can you?
Somebody back
I
there.
got a time buffer for like.
Okay, well what are we gonna buffer to?
I mean, basically whatever you would expect the like highest computation time, so that you don't return the pad early.
Okay, so you're gonna say, I'm always going to take 1,000 milliseconds to return a response, and if I get done early, I'm just gonna like spin or something like that or whatever.
Or just have it check the tag even if the padding does fail.
Good, so you both propose two different solutions. Always check the tag, which means you're always hopefully doing the same amount of work. And what you just described is called quantizing, where you delay to some fixed amount of time. And both solutions in practice are often used. People don't like quantizing because they don't like to make their servers sit. So they went with your solution. Fixed, right?
Can you map the padding as well?
You could, but in TLS, where they were stuck with this protocol, that would require changing every TLS client's operation and every server. You couldn't like just patch one server. You'd have to change the whole protocol. So yes, you could start to map the padding and do some sort of stuff that would fix the protocol. Although, maybe we should just use a different way of doing this instead of, if we're gonna make changes, we should fix it right. But yeah, maybe mapping the padding would have helped a bit. But they couldn't do it. So they had to add these Band-Aids. We have one Band-Aid which is always, always return the same error, but it got blown away by a timing issue. And then now we're trying to add another Band-Aid, which is always check the MAC even if the padding looks bogus. Does anyone see any problems with that? How could that leak any information? It seems great. You're always checking the MAC. Anything? What are you checking the MAC on? Okay, the message. What's the message? You've got a blob of bytes coming in. You decrypt it. You've got a blob of bytes. What's the message? Where's the message? Tell me how I find the message in this thing.
First, remove the tag.
Okay, wait, there's one step you forgot in there. First, remove the what?
The padding.
But the padding's broken. How much padding is there? If the padding is all screwed up, I can't remove the padding because it's all broken and garbagey. I don't know where the tag is. I don't know where the message is. So in fact, wow, what am I going to put into my MAC check? What am I going to feed into the MAC? Just whatever. I like just whatever. What is just whatever? Give me a concrete just whatever. What's that? Well, you need to feed in some bytes. So what bytes are we going to feed in? I mean, you can put, what do you mean by length? Like just a length byte? Like we need to.
Length of the tag.
Okay, but no, so we're definitely going to have to check the tag. But let's say this message could be anywhere from 1 byte long, in the simple case, let's just assume, to a full 15 bytes long. How many bytes of it? But we don't know because this padding's all screwed up. How many bytes are we going to, which bytes of the message are we going to feed into this? Which bytes of this whole thing that we got are we going to feed into this MAC function?
The first, like, whatever minus how long the tag would be.
Oh, so doesn't that mean we're basically just going to assume if the padding's broken, we're just going to say, you know what, let's assume the smallest possible padding. And we're going to feed in as much as we can. And we're just doing this anyway to kill time, right? It doesn't really matter if it checks out. We're just doing this to kill time. So that means if your padding was really long, and I send in the message with non-broken padding, right, it would actually only put in a small subset of the data into the MAC function. But if I really screw up your padding, it's going to put in a lot more data into the function. And what is the result of that from my perspective as an attacker?
You can time it.
You can time it. So you have one strategy when I've screwed up the padding, and your strategy when I've screwed up the padding takes more time. So an even tinier leak, and it turns out that TLS allowed up to 255 bytes of padding, and you can see why 255, because you couldn't fit any more stuff into a byte. So that was a problem they had, is that you could have up to 255 bytes of padding. An attacker could maul the ciphertext in such a way, you can even maybe maul the ciphertext to make a big difference in the amount of padding. And this tiny little sub-millisecond leak in timing was enough to figure out whether you were getting padding error or MAC error. And there was this attack, what was it called? It was called Lucky 13 that actually broke modern web servers as of like 2014, 2015. Okay? So these things are really hard to fix. And the answer, the long-winded point that I'm trying to make here, is that if you use the wrong composition of MAC and encryption, it doesn't just hurt your your authentication. It actually can hurt your confidentiality. Down here, we showed that it hurts your confidentiality, but kind of in like a lame way, because it only lets you learn like one thing about the data. But up here, it actually let me completely decrypt your data depending on the encryption scheme. That's really bad. And this wasn't known to cryptographers back in 2001. We kind of thought that like authentication and confidentiality were separate problems. But what we learned is that in some cases where you have a decryption oracle, we have, basically we have a different, we have basically the problem can be like put together in different ways. Sorry, that flash totally threw me off. So basically what we learned is that these two properties are tied together in interesting ways, okay? All right, so that's basically how a padding oracle works. Now, there's a method to my madness. There is a reason that I'm teaching you about padding oracles, and you're going to learn about that soon. So please don't just take this as an informative, kind of fun exercise in class. Like, remember it. Try to think about it, because you're going to have to think about it a lot soon. But this is basically what padding oracles are and why these things matter. Okay, good. Let me see where I was. I think I had some other stuff on here. Okay. Not too much more. Okay, yes, there is one more thing I want to talk about. So we've talked about, I want to just really beat this authenticated encryption thing to death. All right, we have talked about attacks on using the wrong mode of authenticated encryption. Well, what does it mean for something to be secure if it's using an authenticated encryption scheme? Now, I've already given you a definition that tells you what secure means in the world of regular encryption schemes, where we didn't care about this kind of mauling of messages and chosen ciphertext attacks. What does it mean for an authenticated encryption scheme to be secure? Can somebody give me an idea of how we might take, remember our semantic security, also known as IND-CPA definition. Can somebody remind me of how that worked, and now tell me how I can patch this up so we add some kind of equivalent, some kind of way of capturing authenticated encryption security. So what's the first part of authenticated encryption? It's a game of IND-CPA. It's a game between a challenger and an adversary, right? What's the first move? Quickly, you guys should know this. So,
Send message to a chatting.
Good, okay, so wait, so send messages, M, and get back what?
C.
C, okay, so C is equal to enc under K of M. So we have a key, by the way, that this guy picks. All right, great. And then what's the next phase? This happens many times. What's the next phase?
M1, M2.
Yeah, or let's say M0 and M1. A little convenient. Okay, and what do we get back?
The encrypt of MP.
Good. Crypt. We'll call this C star just because it's convenient. Is encryption under K of M sub B, where B is a randomly sampled bit chosen by the challenger. And of course, our job at the end of this is what? Is the adversary. What do we want to output? Okay. Well, we're going to basically output B prime, and the win condition is if B equals B prime, we win. All right, this does not handle authenticated encryption. It would not, for example, you could have a scheme that's totally secure in this definition, but that falls apart catastrophically under this padding oracle attack we just described. So how do we update this definition to make it handle things like padding oracle attacks, which seem really bad? What do we want to add to this definition?
The adversary should provide make a message that looks like the challenge.
So maybe, I agree that could be the case, but I'm not really worried just about padding oracle attacks. What is the capability that we used when I showed you this padding oracle attack? What was the base requirement that the attacker had to have in order to make this work? Yes?
Just gaining one bit of information.
Gaining it from what? From whom?
From the challenger.
Good, and how did they gain it? What was critical?
By sending a lot of queries.
And what were the queries made up of?
Modified, modified messages.
Modified.
Ciphers.
Modified ciphertext. So I have to be able to send a ciphertext in and have somebody do what to it?
Check. Validated.
I like those words, but there's another word that I'm looking for. More. Decrypt. Okay, so I'm assuming when we talk about authenticated encryption, we're building it by putting together a MAC and encryption scheme. When I talk about how you would, first you would decrypt and you would check the MAC, I'm going to call all of that stuff decryption. So when we do authenticated encryption, the decryption process also will involve checking the MAC and doing all that stuff. Okay? So what does our definition have to add to simulate or to give our adversary that kind of power? What's missing here? Can our adversary ask the challenger for the decryption of any message? No? Okay, good, great. So what do we want to give them? How do we want to fix that?
A message except M0 and M1.
Oh, I like what you're thinking. Okay, but why not let them? Right, well, they're not going to decrypt messages. They're going to decrypt ciphertexts. So let's say we give them as well an extra option. In fact, I don't even care if they mix these up. They can send in M for any M they want, or they can send in a ciphertext, any ciphertext they want. And if they send in a message, so they can basically say, enc, comma M, or decrypt ciphertext. And if they ask for the encryption, we'll still give them back the encryption under K of that message. Or if they ask for the decryption, we'll give them back the decryption under K of that ciphertext. Okay, so we've now given them a decryption oracle. So the challenger is now decrypting arbitrary ciphertext for them. Does this get us all the way there? Can you do a padding oracle attack? If you're an attacker and you've implemented your scheme using this, it's got the same flaws in it that the TLS encryption did. Does this definition allow the attacker to run a padding oracle attack? Yeah.
It doesn't really give the info the time that it took to decrypt or
Well, you're right. I agree with that, but maybe we'll find some way to reveal that kind of stuff. Okay, so we'll leave that aside for a second. Okay, so this definition that I put up here has a name. It's not the definition we want to seek out, but it has a name. And its definition is called a non-adaptive chosen ciphertext attack. So remember, we started out with CPA, and now we've gone to CCA, which means chosen ciphertext attack, and we call this non-adaptive chosen ciphertext attack, we call it CCA1, because it's a weaker definition than where we're going to go. Just don't worry about the details right now. Okay? So this is non-adaptive. Why is it non-adaptive? This thing is also sometimes called a lunchtime attack. And the reason it's called a lunchtime attack is it models a real attack that occurred to some cipher machine where the cipher machine operator was sitting at their desk in the morning. They were doing all kinds of encryption and decryption, and then they went out to lunch, literally, and they forgot to lock their office door. And somebody actually snuck into their office and used the cipher machine a bunch to decrypt and encrypt ciphertexts, which is this part. But then later on that afternoon, an actual message that mattered was sent, and the attacker didn't get to come back in. So they basically only get to attack here at lunch, but the really important message that we want to decrypt is down here, and unfortunately the lunchtime is over. So this is called a lunchtime attack because you only get decryption capability up here and not down here. All right, so what else? Yeah?
Get decryption capability after you send the
Good, so this is key. So we need to add a second phase of decryption capability where basically we say, okay, in fact we're just going to repeat this. I'm going to call this the challenge phase, not, I'm sorry, that's totally stupid, no. I'm going to call this the query phase. And I'm going to let you run the whole query phase again. Same messages again here. I just don't want to write it all out, so I'm just going to say repeat the query phase. Is this a good definition? So now we get to talk to our decryption oracle. We get to ask for encrypted messages. We can do anything we want, but we get to do it after we've gotten the encryption of M sub B. Is this a good definition? Does this now give our attacker the power they need to run a really powerful attack? There is a problem with this definition. There is a really big problem with this definition. Yeah, that's a crappy definition, because the adversary in this game is always going to win. They've gotten C star, and I just said they could decrypt it. Okay, not a good definition. How do we fix it? How do we remove that one flaw? Yeah.
When they ask for a decryption in the bottom, we don't send them the message back. We just say,
nope, I'm going to give them the decryption of anything they want.
okay.
Except for one thing. Because if I give them the decryption of that one thing, it's a pretty stupid definition.
Except C star.
Good. Okay. Query phase is exactly the same as the first query phase, but you can't decrypt C star. We're just going to say that's a rule. If you send me C star to decrypt, the challenger is going to say, no way, sorry, failed. That's the only difference. Yep.
What is C star? I can't see.
Oh, I'm sorry. C star is the challenge message. It's the encryption of M sub B. It's the thing you're trying to, it's M sub B encrypted, you're trying to get B. And so this is really the message you need to crack open. Okay, so you are going to be allowed to query any decryption of any message you want. You just can't actually ask for that C star message. That's it. Do we like this definition? I hope we like this definition, because this definition is actually something that we call an adaptive chosen ciphertext attack, also known as CCA2, also known as the midnight attack. Don't ask me why. Well, you can probably guess why, right? Because the hypothesis here is that an attacker gets to break in at lunchtime, use the decryption machine. In the afternoon, an important message gets sent, and they get to come back at midnight, and they get to decrypt more stuff. But for some reason that in this analogy doesn't make a lot of sense, they can't just decrypt the message that they actually want to decrypt, whatever. Okay? This seems like a crazy definition to people. People get really weird about this definition, this chosen ciphertext definition, because it seems really artificial to them that you're giving somebody the ability to decrypt any message, except for C star, except for the message that they actually want to decrypt. It seems really artificial. The only reason, the actual way you should think about this is what we're doing here is we're giving the attacker as much power as we can possibly give them without the whole game becoming stupid and meaningless. So one way, if you look at this padding oracle attack I gave you, think about it this way. So the attacker in our padding oracle game, with this padding oracle vulnerable scheme, gets a ciphertext, and then they send in lots of decryption queries. Okay? They can send in anything they want. But they're not getting the full decryption of the message. So in a sense, that game, the attack there is actually a little weaker than this. Here we're actually giving them everything. Right there they just get a function of the message. Here we're actually giving them back the plain text. So this definition is even more powerful in a sense. But if a scheme can survive this definition, if a scheme can be played against all adversaries in this definition, and all adversaries can't win, except with probability 1/2, then I claim to you, and I don't have enough time to prove to you, but I claim to you that if a scheme is secure under this definition, it will also not be vulnerable to our padding oracle attack. And that's because we've given the attacker in the scheme tons of power, and the real vulnerabilities like padding oracles we run into are really just a subset or a reduced version of this game. Okay? And so that's kind of it for today. We're going to move on from here. We're going to review this a little bit on Monday, or Alicia is. We're going to talk about public key encryption and hash functions.